So we're going to do derivatives as rate of change and derivatives of function. So here we're going to start defining. So the first derivative function is, so here, given the difference quotient, you've done this before, is so you have f of x plus h minus f of x all divided by h, and we call this the difference quotient. And your teacher may or may not have hinted that this will turn into your derivative function. Well, how do we take the derivative function? Well, the smaller that h was, the better that average rate of change was for a given point, right? But here we're going to take that h and send it to 0, and we're going to make that an instantaneous rate of change. And so that's what the real differences are. So let's just go ahead and write out some of these differences. All right, so let's go ahead and do that. So here we're going to have the difference quotient. And here we're going to have the derivative function. We'll just write derivative. All right, so the difference quotient gives you the average rate of change. And the derivative will give you an instantaneous rate of change. And so here, so here we have delta our function over delta x. And here delta means some difference. Here we're going to have d of our function dx. And so this means, so here this delta can be of any size. And here we mean infinitesimally small. I mean, we mean non-zero, but so small it's you can't really measure it. And so that's what we're kind of doing here is we're saying that difference is so small. And so this h represented how far we were apart. So here, this gave secant lines, right? So the difference quotient gives you a secant line because you're going to have some h here, right? Some h here. And so we're going to try to determine the average rate of change between these 2 points, and we just draw a line in between them, right? And the slope of this line was your difference quotient, right? And here, this is the average rate of change between here and here. Now, as we bring this in, let me just do it in a different color, right? As we bring this in to here, we're approximating the slope of this line more and more until we eventually get to here, which we have a true tangent line. Straight through this. And so as we brought this closer and closer and closer in, as we made h smaller and smaller and smaller, it approximated the slope, the tangent line here, closer and closer and closer. And so we went from an average rate of change to the instantaneous rate of change. Okay. And so, can you zoom out, please? I love how it's always zoom in and zoom out. I can't. And so here we have this. And so there's the difference. The difference quotient is an average rate of change, which gives us a secant line. The derivative functions, we're gonna take that average rate and contract it into a single point, right? We're actually going to calculate this by using this formula right here. Okay. And the small d's mean total differentiation. We're not going to do the other one quite yet. And the capital deltas, right, means, and this is delta, which means difference. So here's this page. All right, so let's do the next page. Let's actually calculate this. Let's actually crunch through this. I want to find, let's find this. So we're going to find the derivative function for f. So this is my f, so we're going to find the derivative. So we're going to write out our function. We're going to send h to 0. And here we're going to have the limit of f of x plus h minus f of x all over h. And so this is equal to f prime of x. And so we use a little prime symbol here. Hold on, let me clean that up. use this little prime symbol to mean derivative function. So let's plug that in. So we already have the limit as h goes to 0. Here we're going to have 5 of x plus h squared minus 3x plus h plus 1 minus the quantity of 5x squared minus 3x plus 1, all divided by h. Go ahead and take the limit as h goes to 0. And go ahead and expand this out. So I'm going to get 5x squared plus 10xh minus or plus 5h squared. So remember, if I FOIL this, I'll get x squared plus 2xh plus h squared. So get this minus 3x minus 3h plus 1. Go ahead and move this. So I have minus x, 5x squared. This becomes plus 3x minus 1 all over h. So once we get here, we can cross some stuff off, like you did in the difference quotient. So this cancels out with this cancels with this, and this cancels with this. And so here, go ahead and write this on another line so I don't lose people. We have 10xh plus 5h squared minus 3h all over h. And here we can cross off an h. And this is going to equal the limit as h goes to 0 of 10x plus 5h minus 3. And here, we can just directly plug this in, and we just get 10x minus 3. So what do we have here? We have our derivative function. It's equal to 10x minus 3. So find the derivative at 1. Well, here, we want to find the derivative once. Once we have the function, we just plug it in. And so we have 10 minus 3. Oops, 10 times, let me be very clear what I'm doing. 10, I'm plugging in a 1 here, minus 3, and we get 7. Okay. All right, so here, let's look out, let's zoom down for a little bit. Notice here, I have at 3. And if I drew in my tangent line, notice here the slope of this line is 7, right? The slope here is 7 for this tangent line. Let me zoom on in a little bit. So here the slope of this is 7. Okay. And so this derivative function tells me the slope of any tangent line at any given point for the function. So given a function, I can compute the derivative function. And after I compute that, I know the slope of all the tangent lines for that. Now, why is that important? Because you know the rate of change at any point, right? You notice the instantaneous rate of change is changing at all points, right? So it's always changing. And so it's really useful to know what's it changing at a given point. And so that's what the whole point of this. I'll go back pages at the end for those who've missed up. All right, so let's answer the question. So where's the derivative equal to 0? So here, where's this equal to 0? Well, we just solve for this. We just say 0 is equal to 10x plus 3. Well, if I solve for this, I'll get minus 3 equals 10x, or x is equal to, oh, hold on. I put a plus here. Is this plus? No, this is negative. This is minus 3, this is plus 3. So I get 3/10. And let's look right here. Zoom on in. Notice that our tangent line of the point I've drawn is 0. So the slope here is 0. And when does that occur? Well, if this is 1, this is indeed at 3/10. Okay. So this is part C. of my notes. This is part B. And so to me, it makes a lot more sense just to calculate this number directly and then answer questions that come from it. Your book will have you answer this question first and then go back and discuss how to answer that. And to me, that seems a little backwards. So here's this page, and then we'll go to the next one in a second.
On part B, why do you plug in 1 instead of 0?
Oh, so here, part B, I want to find the derivative of f at 1. Just what the question asked, right? And use this to write the equation of a tangent line at 1. Oh, I guess I didn't do that part. Let's do that part real quick. Well, here I know what the slope is. The slope here is 7. Well, what's my function at 1? Well, my function at 1, if I plug in f of 1, here if I wanted to find this line, how would I find this? Well, here I know the slope, right? Let's go ahead and find a point on this line. Well, the point on this line is 1 and 3. How do I know that? Well, here if I plug in 1, and then I'll plug in f of 1. Well, f of 1, if I plug in 1 into this original function here, I'll get 5 minus 3 plus 1, which gives me 3. And so this is just 1, 3. So here I have a point, I have a slope. So m equals 7, and here you can just use y minus y1 equals mx minus x1 to determine the slope of this line and determine this line. Well, I'll actually calculate it with you next time. So let's go ahead and do the next one. All right, so here, oh, yeah, so this is how you calculate the slope. Am I missing something? No. All right, so let's do this. That way it should give you enough to start the homework and get through most of it once I post it later tonight. All right, so we're going to use the first derivative to calculate this. And in fact, we're going to do this one twice. We're going to do it the first way, and then we're going to do it using, there's an alternate formula. The alternate formula, I wrote it from a different, I had it from a different book, and then I was like, nope, we're going to just change it to this. So this may look different on your notes. If it does, just go ahead and switch it to this, right? This is the alternate derivative formula, where you take a function minus the a, and then you move the function infinitesimally close to that a. And so this is literally x, the change in the function. So this literally says the change in the function, right? So x minus whatever you moved it by, right, over the change in x, and then you're going to take that distance between these two and send that to 0. So this is like taking that line, squishing it in. So this is the alternate. Do both of these work the same? Yes. And I'll show you that they do. So let's do it twice, and then we'll call it good for the day. So let's start with the normal, boring way. So f prime of x is equal to the limit, as we're going to still do the h approaches 0 of f of x plus h minus f of x all over h. And in our case, this will look like the limit as h approaches 0. H is look a little more like ends of x plus h. Oops. H cubed minus f of minus x cubed all over 3, or h, sorry. So in order to do this, we just expand out this. And you should know this from binomial expansion that this is x cubed plus 3xh, oops, 3 squared h plus 3x h squared plus h cubed minus x cubed all over h. And this is just how to expand a binomial. If not, you can always just type it in. So this cancels with this. And then I'm left with h's. And so here I can cancel 1h here, 1h here, 1h here, and 1h here. And so here I'm left with the limit as h approaches 0 of 3x squared plus 3xh, because I only have one left here, plus h squared. But now I can just plug in directly, right? And this is just equal to 3x squared. So here I can just plug it in directly, and here, this is my derivative formula. My derivative formula of f of x, 3h squared. All right, let's do it the other way in the last 3 minutes of class. And the other way is, once again, from down below. I changed it from what I had. I like this way a lot better. X goes to a of f of x minus f of a over x minus a. And so in this case, we're going to have x cubed minus a cubed divided by x minus a. Oops, and I forgot my limit. The limit as x approaches a. All right, so now I have a difference of, whoops, that should be cubed. I have a difference of cubes. A difference of cubes factors in the following way. So I have x minus a. And then here I'll have, see if I remember this correctly, should be x squared minus, or no, since this is minus, this is plus, x a plus a squared all divided by x minus a. So this is just the difference of cubes. You can look it up. Here, if I cancel this out, I'm just left with the limit as x approaches a of x squared plus xa plus a squared. Here I can just plug it straight in, and so here I get x squared plus x times x, because I'm gonna plug in. Hold on, I think I'm doing this. That's fine. There's one small little problem with this, isn't there? Hold on. I think even after I rewrote it, I wrote it. It should be. Hold on. Yeah. This x should be an a. Sorry about that. So here, this becomes, everywhere I see an x, I'm going to plug in a. So I get a squared plus a x a times a, which is a squared plus a squared. So this is equal to 3a squared. So f prime of a of 3a squared. These are essentially the same. The only difference here is what variable you have. And they give you the same formula. Okay. All right. Well, that's time. So we'll finish the rest of these sections, the rest of the notes next time on Monday. Yeah, I can zoom out. The homework's not due until next week, so it's just 1, 5, 1, 6 this week. Oh, how does this for the top one? Oh, here, if I plug in h equals 0, 3x times 0 is 0, and 0 squared is 0, so the only thing that survives is the 3x squared. Okay. Go ahead and cut it right there. Yeah, and then it just all kind of falls out nicely. So let's start here. So let's start. So we're going to take the derivative of this. So we're going to find the derivative formula of this. And so the derivative formula, as you remember, make this look a little bit cleaner. So our derivative formula is we take the limit as h goes to 0. This is the derivative formula I'm using. You can use either. There's two options. I think the book starts with the other one and then goes back to defaulting to this one. And here we're going to take g of t plus h, minus g of t, and divide that all by h. And so remember, this is our difference quotient, and we're going to take the difference quotient. We're going to find the limit as we make that as close as possible. Because remember, derivative tells you the instantaneous rate of change of a function. That's what it tells you. So we do this, and so we just plug everything in. So here the limit as h goes to 0. All right, let me zoom out. Hold on. I have my little cheat sheet. Make sure I do this correctly though. So here I'm going to have t plus h over t plus h plus 3. Because here I'm going to take in, everywhere I see t, I'm going to plug in t plus h, right? Minus t over t plus 3 all over h. All right, so for this, the best thing I would do is just kind of clear out the fractions. And to clear out the fractions, we're just going to multiply the top by t plus h plus 3 times t, oops, t plus 3. And then we're going to multiply, well, we multiply on the top, we have to multiply on the bottom, because this makes this multiplying by a 1, right? Which I'm allowed to do. So we're multiplying top and bottom by this. So when I do that, I get the limit as h goes to 0. Well, this crosses out with this, and so I have t plus h times t plus 3 minus t times, well, this crosses out with this, and so I'm left with this, t plus 3 plus, or t plus h plus 3 all over by h of t plus h plus 3 plus t plus 3. Okay. All right, so what do we do from here? Well, what we do from here is we go ahead and expand. So we expand this out, so I get t squared. And then I get plus 3t plus th plus 3h minus t squared minus th, and then minus t3, or 3t, I guess would be better, all over h plus t h plus 3 plus t plus 3. And do not forget, like I did, the limit as h approaches 0. All right, but here a lot of things will cancel out. So this cancels out with this. T and H cancel out. The minus 3t and the minus 3t cancel out. Here, now the only thing that's left on top is this. You can cancel out an h here and an h here. And so this is left in me with 3. Yeah, I'm okay. I'm going to actually do 2 steps. 1, 3. And then here we can safely plug in. And since we're no longer dividing by 0, because the 0's gone here, we can safely plug in 0. So this is t plus 3 plus t plus 3. So this is t plus 3 squared. Okay. Anyone confused how I went from this step to this step? Doesn't seem so. Okay. if so, please write it in chat. So g prime of t is equal to 3 over t plus 3 squared. How do you get t plus 3 squared? Oh, that's a good question. So here, I'm sending h to 0. So this goes to 0, right? I couldn't send h to 0 until I crossed it off. If I wrote the intermediate step, it would be the limit as h goes to 0 of 3 over t plus h plus 3 times t plus 3. Now I can safely send h to 0. So this is t plus 3, and then you get it together. Yeah, good question. Very good question. I'm glad you asked it because I guarantee someone else did had it. So we have this. And so now, so we found A. So this is A. B, find g prime of 6 and use this to write an equation to a tangent line at 6. Okay. All right. So here, so g prime of 6, well, if I plug 6 into this, I'll get 3 over minus 6, sorry. This should have a negative sign. Sorry. I wanted to find the tangent at negative, and I forgot the negative sign here. There we go. All right. Here we go. Yeah, because that will match the graph. Okay. So here so here I have minus 6 plus 3 squared. Well, this is equal to 3 over, this is 3. 3 squared is 9. So this is a third. So my slope here is a third. How do I get the point? What this point? Well, here, if I look at the graph, I can say it's minus 6, 2, right? But we can also figure it out. Here, if I take g of 6 is equal to, what was g? Hold on. G is t over t plus 3. Or so g of minus 6 would be minus 6 over minus 6 plus 3. So this is minus 6 over minus 3. So this is equal to 2. So here we have a point of minus 6 and 2, right? So this gives us our point. We know what the slope of the graph is. It's here. It's a third. So here we can just plug it into this. Y minus y1 equals m x minus x1. Here we'll get y minus 2 equals 1/3 x plus 6. And then if I solve this out, I'm going to get y equals to 1/3 x plus 4. And so that gives us our point. And notice here's another point on our graph. And then here we can just draw in our tangent line right here. And notice how that represents the tangent of the line at this point. Okay. All right, so I'll let you write this down for a second as I take a drink. Why is it negative 6? Oh, because I meant to say negative 6 in the beginning. I just picked a point. Find the derivative of it and write the equation of a tangent line at a point. And so here I just picked a point on the graph. If I want to find a tangent line, I have to pick a point to find that tangent line at. Okay. So I picked a value. In your homework, you'll do it for different values. You'll find the equation, then you'll find the derivative, and then you'll say do it. So, okay. All right, let's do the next page. All right, so let's do this again. All right, so we're going to do this again, and now we're going to do it for the square root of x plus 4, and I'll show you the tricks to use for that. And then we're going to find the tangent line at 0. And so here's our graph. We're going to find the tangent line here at 0. So let's do this. So here we're at x plus 4. So q, in this case, q prime of x is equal to the limit as h goes to 0. And here we're going to have, let me write out the formula. Q of x plus h minus q of x all over h, which is equal to the limit. When I went through high school and college, when we were doing this, I always got in trouble. It's like, because I never rewrote this. I'm like, it's like, it's the same, right? And I just never rewrote it. It was just terrible. Please write this each time. All right, so here we'll have x plus h plus 4 minus the square root of x plus 4 all over h. All right, in order to solve this one, every time you have one of these limits with a square root, 99% of the time, well, maybe not that much, but 90% of the time, you're just going to multiply by the conjugate. So here it's minus, so we're going to add a plus of x plus 4. We've done this before, and you'll probably do it again, right? And so this is the trick you always use. So every time you have square roots, when you have limits, you almost always do this trick. Okay. And so what this does is it clears off the square roots up top, because this times this gives you just x plus h plus 4, and then this times this will give you, this times this gives you a positive version, this times this gives you a negative version, so they cancel out, and this times this will just give you the negative version of this. And so what we get at the end is x plus h plus 4 minus x plus 4. Okay. All over h. Uh-oh, my thing's getting crunchy. I know how to fix that though. We just hit File, Export to PNG, so I have it. Yep. Save. Yep. And we hit the bye-bye button. Ta-da! And presto, it gets less crunchy. See? I will upgrade my computer, but I use a Mac, and so I'm waiting until they come out with the desktop ARM chips. I guess they already have the Mac Mini, which is already pretty amazing, but I'm gonna wait until they have like the bigger desktop of it. So I'm waiting. Upgrade. All right, so we have this. So, oops, what did I forget? I just give a lecture on do not skip writing the limit. And what do? I skip writing the limit. Ta-da! So here we just did multiplication and cross. Now what can we do? We can cross stuff off, right? Notice that here, if I distribute this real quick, I'll go ahead and distribute this. Distribute that negative. Get rid of the parentheses for 1 second. Here I have x, positive x, this, negative 4, 4, and I can cross off the h. And so here, what am I left with? I'm left with the limit as h goes to 0 of 1, right? Because I crossed everything off. 1 over square root of h plus 4 plus the square root of plus 4. And in this time I won't skip the step. So here I'm going to take the limit, and here I can just plug it in safely, right? Here I can just take the limit by plugging it in. If I plug in here, does anything go wrong? No, right? And so here I have 1. So here I've actually taken the limit. I'll have x plus h plus, x plus 4, sorry, plus the square root of x plus 4. So that's equal 1 over 2 the square root of x plus 4. Okay, and that's our answer. And that's equal to, once again, that's equal to, so here is our derivative function. Okay. Wait, why did you cancel? Oh, here, let's go back to this point. Let's go back to, no, I want the bigger. Let me do this slowly here. So here I had x plus h plus 4 minus x minus h over h. Okay. So here, I'm going to use the negative x to cross off this x. I'm going to use the, oops, that's a 4. That should be a 4, not an h. Sorry. Here, I'm going to use this positive 4 and negative 4. And so here, my next step, my little sub-step, which I'm skipping right here, is h of h plus all this stuff, right? Then I'm going to cross off this h with this h, leaving me only the 1. Okay, so here's where the 1 comes from. Then I get rid of this h because I take the limit. I take the limit by plugging it in, right? And so here I plug it into this becomes 0, so I get x plus 4, which gives me this. All right. Hopefully that answers where I cancel the h. Depends on which h you're talking about, right? Here I cancel everything on top, and so I have h and h, and so these are factors in this, and so I cancel this out. Here I get rid of this h because I plug in 0 for it. Okay. Would it be wrong if we left the true roots separate? If you left it at this step, I would not mark it wrong. Okay. Can you explain? Can you explain why it's 2 times the square root? Oh yeah, here I have x. I have x plus the square root of 4 plus x plus the square root of 4. Therefore, I have 2 times of whatever this is, right? So it's once and twice, so I just put it together. It's kind of like if I have x plus x, you make it 2x. Just this time, it's a more fancy function. Okay. Once you plug it in, the limits so once you plug it in, the limits no longer needed. So here so from this step here, let me do it in, I don't know, round. In this step, I have not taken the limit. In this step, I've taken the limit. And so the difference between this step and this step is I take the limit as h goes to 0. Well, in this case, this is a perfectly safe place just to plug in 0 for h. And so I just plugged in 0 for h, and that's taking the limit, and therefore I no longer need to write it. Okay? Because I've done the limit at that point. Here, from this step to this step, I'm just simplifying. Okay, hopefully the square root one tends to dig out all the questions. So I'm glad we have all the questions being dug out. Okay. All right, so let's do the last little step. So I want to find the tangent line is at 0. So here, I know what the point is. It's 0, 2, right? So here I already have my point of 0 and 2, right? Another way of finding that is if I plug in 0 for x, I'm going to get 2 for q. And so here we get 0, 2. Here we're going to find our slope is 0. And so here we're just going to take q, not g, q prime of 0 is equal to 1 over 2, 0 plus 4. Well, this is equal to 1 over 2 square root of 4, which is equal to just 1, 4, right? So here I can write out my equation, which is y equals 1/4 x plus 2. And so here, my next point, and I can just draw in my tangent line. All right. So now let's do the next page. Let me give you a second to write that down. I'll take a sip. Okay, now let's go to the next page. All right, so let's talk about what a derivative means and what everything's going. So here we're going to start the particle start moving from right on along this horizontal line. Its position s is given after t seconds, as in this figure. So here we're going to talk a little bit, get a more concept idea of, instead of just calculating numbers. So here I have some particle p, and here I'm going to be traveling in its position s, right? And so wherever this particle's at in t seconds, and so as the particle moves to the right, it's positive movement. If it moves to the left, it's negative movement. And so here, this is where the particle. So we're going to start at 0. The particle is going to move. Let's just kind of draw this graph of what's happening. So here, we'll go to here to 4, right? And then I need here at 3. So here, so when we start, this particle moves. In 1 second, it goes to 4. And then it sits there for 2 seconds until we're at 3 seconds. And then it goes slowly back over the next 2 seconds to 3. Then it sits there for a second, and then it moves forward to 5. And so then it moves forward to 5. Okay, so that's the movement of the particle. So when's this particle moving to the right? Well, it's when it has a positive slope, right? So when the slope here is positive, and this slope is positive, it's moving toward the right, right? So this position is going to the right. So we're going to write from 0 to 1 seconds, union from 6 to 8 seconds. Okay, so this is the interval for time in which this is moving. When's the particle moving to the left? Well, it's only moving to the left or going in the backwards direction while we have a negative slope. Well, that's right here between 3 and 5 seconds. When's the particle standing still? Well, twice, between 1 and 3 seconds. Union, and between 5 and 6 seconds. Okay. And so what is this? So a positive slope means the particle is moving to the right. Negative slope means moving to the left. And when it has 0 slope, notice the slope here is 0, or its derivative would be 0. It's standing still. But this is really what I wanted to focus on. Is like given a graph of a function f of x, can I graph the corresponding derivative function? Yes. And also you can do the reverse. Given the derivative, you can graph the corresponding function, right? So you'll do these a little bit back. When is the particle standing still? So would I use close brackets? The answer here is no. And I will explain why in I'll explain why now. So here, let's get rid of this. So here, when is it moving to the right? Or in other words, when's the derivative of this function? When's the derivative of s of t greater than 0, right? That's when it's moving to the right. When it has a positive, in our case, we'll call it velocity. When it has a positive velocity. Notice here, this is a hard turn. And so we'll talk more about this on the next page, but I'll might as well go over it now. Here, if you have a point or a sharp turn, your derivative will not exist, right? Your derivative won't exist, and so you will use the you're going to use the parentheses, right? Okay. Oh, someone asked real quick from how did you get to where did you get to 2 for the coordinates? Oh, let me just answer that real quick before I move on. Here, how did I get the 0 and the 2? Well, I want to find the tangent line when q is 0. So if q is equal, if q is equal to 0, here I'll have x of 0 plus 4, which is equal to square root of 4, which is equal to 2. So the point here is 0, 2. That's where I got that point from. Okay. So that's where I got that point from. Or you can just, in this case, I pulled it from the graph. So you just plug it in. So this is your x value. This is your, in this case, q of x value. This would be your point. All right. So at this point, the derivative doesn't exist. At this point, the derivative doesn't exist. And here, all the derivatives don't exist at that point. And the reason is, if I thought about it for 2 seconds, if I took the limit and I was walking in this way, what does it look like? Well, it's the slope. The slope looks like here 4, right? Well, if I'm walking this way, what does the slope look like? It looks like 0. And since these don't agree, the left limit and the right limit won't equal each other. And I'll show you that on the next page in more detail. So let's go ahead and do that. So here, notice here my slope is 4. So my derivative function, right, might be, because my s prime of t is equal to velocity, right? So our position, which we use s for in physics, I don't know. Someone explained it to me once, and I remember, and then I forgot, and then it's like, I guess it kind of makes sense, right? And so here, the derivative of position is velocity, right? And so here, but the derivative just gives you what's the slope of the tangent line. Well, this is always going to have the same slope of the tangent line, which is always going to be 4. So my rate of change, instantaneous rate of change of all this is always 4 units. And so for here, it's 4, and we just draw this in. We have an open circle here, because I do not know what the velocity is at this point. Here, I have a slope of 0, right? So my slope here is 0. So here I have 0, so open circle, 0, open circle. Then I have a negative velocity of a half, right? Because the slope here is minus a half. I guess I should have done this one more down, but that's okay. We can just draw this in, open circle a half. Here goes back to 0 for a second, and then it goes up to 1, right? That's my slope here. Okay. So given this, given this, you just, if you're given the particle, if you're given the actual function, just find what the slope of the line is at these points, and that's will tell you where you're at here. If you're given this, start at whatever initial value you said, and then here for this, I'm going to have a line of slope 4. Here I have a line of, then I have a slope of 0, slope of negative a half, slope of 0, and slope of positive 1. And then you can draw this in. So you can go back and forth. Okay. All right, but let's explain why does the derivative not exist here. So let's look at this real quick. All right, so we have 2 more. So if a function the function is called differentiable at a if the derivative of the function at a exists. If the derivative of an is differential in the open interval a through b, we say it's differential for every number on that interval. So given this, or to infinity or minus infinity, if a function is differentiable at a, then the function is continuous today, but the reverse is not true. The reverse is not true. Let me show you this. Let's look at this graph real quick. So here, oops, now I'm getting crunchy again. Hold on, let me clear out some stuff. Explorers PNG. Save, replace. And don't save. I might as well get rid of this too. Save, replace. And get rid of this. We'll get rid of all my crunchiness. All right, so here, let's look at the graph of this thing. It comes in. Oops, let me just cheat my face off. All right, so here's the graph of the absolute value of x. Okay, so where is this function differentiable? So let's actually take the limit of that. So we're going to take f prime of x is equal to the limit as h approaches 0 for x, f of x plus h minus f of x all over h. Here we're just going to plug that in. So I have the limit as the absolute value of x plus h minus x all over h. And this we're going to take our limit as h goes to 0. So here, oops, nope, I lost my blue. No. So here, let's look at if x is greater than 0, right? Because here we haven't really defined this. If x is strictly greater than 0, then this will simplify to the limit as x plus h. Oh, so here we're strictly greater. So if this is greater than 0, this is less, really close to 0, right? Really close to not exactly equal to 0. So here, if this is positive and this is positive, so we can just get rid of the signs, given that x is greater than 0. H approaches 0. And the same thing with the limit as h approaches 0 of h over h. So this is equal to 1. Okay. And does that match what we have here? Yeah, remember here, the slope is 1 for any values of x greater than 0. So that makes sense not only numerically or analytically as we solve for it, but graphically. All right, so when x is less than 0, so here if x is less than 0, this is equal to the limit of h goes to 0 of minus of x plus h minus x. Because here, if this was less than 0, if x is less than 0, I'm going to take the opposite of that. And this is less than 0, I'm going to take the opposite of that. So here, by doing such, I get minus x minus h plus x all over h. Oops, I forgot my limit. And let me write that in. Wow. Get on the right layer. Limit as h goes to 0 of minus x plus h minus, or plus x all over h. This cancels with this. Oops, that's supposed to be minus. Remove the negative sign in. That's minus h. So this gives me the limit as h approaches 0 of minus h over h. And so this is equal to 1. Or minus 1, sorry. Because this cancels with that and just left the negative 1. So let's look at the limit as x is 0, right? So x is 0. We're going to look at two limits, right? We're going to look at the left-hand limit and the right-hand limit. So here is x goes to 0 plus, and then the limit as, so x goes to 0 plus is equal, hello, that's not what I wanted. I want my brush. So here, we come in from the right side. Yeah, we're coming in from the right side, so from the positive values. This limit of x of 0 plus is going to look exactly like this, right? Because here, if I take the absolute value of x plus h minus x, here, if I'm coming in from the positive values, right, as h is positive, and we're setting x equal to 0, that means this is slightly positive, this is slightly positive, and so this over this will be, of course, 1, right? Same reason here, same exact reason here. Here, if I take the limit as h approaches from the negative side when x is 0, right? Here I get x plus h over this will be slightly negative, or this will be 0 and 0, so this is just slightly negative, which becomes slightly positive. This is slightly negative, so this becomes minus 1. So seeing how these don't match, this limit, the limit as h goes to 0, does not exist, right? So if I'm strictly positive, if my x is strictly positive, right, I have my slope here of 1, right? Here I have a slope of 1. Here, if I'm strictly negative, I have a slope here of 0, or negative 1, right? I have a negative 1 slope. But what's my rate of change here? Well, if I look slightly on this side, it looks like negative 1. If I look slightly on this side, it looks like 1. So the actual limit here, the left hand does not agree with the right hand, and therefore it doesn't exist. And so it gets back to the things that can't be true. So this is continuous everywhere, right? Right here, if you have any sharp corners or cusp, or it doesn't work. And of course, you can't have a derivative if you have a break, right? If your function completely breaks, there's no derivative here. So, but the continuous cases, if you have any sharp corners or cusp or anything like that, it doesn't work. Okay. And the very last thing we need to talk about for this section is if f is a differentiable function, then its derivative function is also a function. So it may have a derivative of its own, and so we take the derivative of a derivative. We call this f double prime. So we call this the second derivative. We call it the third derivative and the fourth derivative. And so you can keep taking derivatives of things ad infinitum, right? And so if it says find the second derivative, take a derivative and then do the same process again. Okay. And that's easier seen when you don't have to do the limits. And so I'll show you how to take multiple derivatives of something in the next section. So go ahead and finish writing this down, and then we'll start the next section. Oh, so why is the one with the absolute values and the other is not? So here, well, hold on. Let me answer that question. So here, we're starting here, right? We're starting here. Now, if I make x strictly greater than 0, right? If I make x strictly greater than 0 and h is really, 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 really small, right? I can evaluate the absolute values by saying, well, this is positive, and so it stays positive, and this is positive, so it stays positive, and so what's in here is positive, so it stays positive. What's in here stays positive, so it stays positive. If x is less than 0, right, and h is really, really close to 0, what's in here is negative, and so I need to negate what's inside of my absolute value. What's in here is negative, so I need to negate what's inside my absolute value. And so here I've evaluated the absolute values in the sense that they're forced to be either this way if x is positive and this way if x is negative. Now, when x is equal to 0, we have to go back to this, right? Because we haven't evaluated it yet. Well, 0 of 0 is still 0, right? But h here matters, right? Even though it's really, 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 really small, x is nothing, right? And so h is going to clearly define if it's on one, if I switch from positive to negative or not. And so h becomes the limiting factor here, not x. Right? So x is the main factor here in evaluating this. But once I set x equal to 0, well, even though h is so infinitesimally small, like as close to 0 as possible, it's not 0, right? And so it's either if it's like infinitely close to 0 but just slightly negative, then the absolute value defines it to be negative. And then if it's infinitely small but slightly positive, the absolute value will define it to be positive. And so h becomes the one that becomes king, I guess, for a second, right? Yeah, so that's why. Hopefully that
Okay,
makes a
that's
little
good.
sense.
I'm wondering if h is approaching 0
All
from
right,
the right.
let's open up the next set of notes. All right, so let's go ahead and save this. And put a little star there. All right, so let's save this. Export APNG. Yay. And replace. All right, so let's open up the next one. Someone's trying to talk to me and ask a question. For a mic? Is my mic off? I have no value. Hold on.
Hi.
I have
Hi,
no
can you?
sound.
Hello?
Hold on.
Hello?
Why do I not have? Ah, my headphones are plugged in. All right, try again.
Hi, can you hear me?
Yeah, I can hear you now. My headphones.
Okay.
Sorry.
I was wondering if h is approaching 0 from the right, so it's a positive number, and that makes that first one positive 1.
Yes.
And then the h is approaching from the left, it's a negative number, and that's why it's negative 1.
Yes.
Okay, that makes sense. Thanks.
Yeah, because here, let's just take h to be 0.1 and minus 0.1 just for kicks, right? And x is 0 at this point, right? So here I have 0 plus 0.1 over the absolute value of 0.1 over 0. Oh, no, this is 0. Sorry. X is 0 over 0.1. Well, this is positive 0.1. This is nothing, or this is 0. And so I have 0.1 over 0.1, which ends up being 1. Now let's take x. Let's take h to be negative 0.1, just for kicks, right? So here I have the absolute of 0 minus 0.1 over minus 0.1, right? So here I have the absolute value of negative 0.1. Well, the absolute value of negative 0.1 is 0.1, right? Positive 0.1. And this is 0. So I have positive 0.1 over 0.1. So this is equal to minus 1. And so here, minus 1. But if x is not 0, right? Say x is like, I don't know, 10, right? If x is 10, this will determine if I switch it. This will stay positive, right? And so I don't switch the sign here, right? And then the h is not this big. It's actually really, really small. So it's something you just sit on for a second and think about.